Arrhenius theory is on the agenda today. The gentleman is before us here. He was Swedish, and he did so well discovering things about chemistry that he got a stamp. And even better, he got a Nobel Prize. Not all of his theories were accepted right away, although today they are very much accepted, and no one ever would have believed that they were even controversial. So we're going to look at his work with respect to transition states, rate constants, and activation energies of chemical reactions. The first thing we want to understand is the transition state. Basically, our reactants need to achieve this transition state in order to proceed to products. And only certain reactants are going to meet the criteria. In other words, they need to have enough energy and they need to have the proper orientation when they collide so that they can actually reach the top of the transition state, and it's all downhill from there into the trajectory towards products. So this is the energy hump, basically. We can think of this transition state as if it were the mountain that needs to be climbed in order for the reactants, again, to proceed to the products. This energy transition is represented by the difference between the starting products of the reactants and the apex, or the very top of this transition state. You can see it's measured right here as the difference between these two energy levels. You can think of energy, increasing energy, as being over here on this axis. Arrhenius was responsible for a number of things, but here we're going to be looking at the dependence of the rate constant. So you may recall the rate constant is little k, as a function of temperature. And it's quite easy to see here that as temperature increases, the rate constant increases as well. This can be written as the rate constant is equal to the frequency factor times e raised to the power of the negative of the activation energy over the gas constant times the temperature. What is the outcome of this mathematically? Well, we can say that there's a clear relationship between K and the temperature, as we see over here on the left. There's also a relationship between K and the activation energy. As you can imagine, as the activation energy gets larger, K gets smaller. And as the temperature gets larger, so does the K constant increase. So just to review our variables here, or our constants, R is the gas constant, T is the absolute temperature, and A is something called the frequency factor. You'll always be given that. It basically relates to the degree to which we have collisions in a given reaction. So this is our formula. And we can take the natural log of both sides and rearrange it in such a way that we will once again get a line graph equation, as we've seen before in this course. We will get something in the form that we prefer, which is y equals mx plus b. This will give us a plot, which is, of course, linear. We're simply plotting the natural log of k, which is our y variable, against 1 over t, which is going to be our x variable. We can look at a plot for a given equation. This is the reaction in question here, and if we were to plot the data, we would see that in the form we just spoke of, plotting the ln of k against 1 over t, we would get a straight line. This gives us a slope. The slope is, of course, going down here because our m is negative, and our m equals the negative of the activation energy over r, and our intercept is a. This Arrhenius equation was taken by another chemist who worked closely with him, Van Hoff, and turned into a form where we can compare two sets of conditions. Basically, we're going to have two corresponding k values and t values. Remember, k is dependent on t, right? So we're going to have one k at a certain temperature of T, and then a second K at a second temperature of T. And we can use the 2-point form to calculate the activation energy, for example. Here is how it looks in the 2-point form. I'm not going to read this whole thing. You can just look at it and see what's happening here. May remind you of something. It may remind you of Clausius Clapeyron. It's, of course, a different subject here, but it is once again the use of a 2-point form of the equation to determine certain things within this equation that we want to calculate. We're going to do a practice problem now. And here we are given that K at 25 degrees centigrade is 4.61 times 10 to the negative 1. Temperature in this case, no, the temperature for that one is 25 degrees centigrade. If we raise the temperature to 50 degrees centigrade, our K goes up to 4.64 times 10 to the negative 1. And we want to know what is the activation energy for the reaction. As always, we're going to have to be cautious with our units, because if we're not in the correct units, we will not get the correct answer. So here we are. So the first thing you might want to think about is, what are the units of R? 8.314 joules per mole degree Kelvin. So we're going to have to take our centigrade values and convert them into Kelvin in order to get a correct answer. That's really the only unit we have to worry about right now. Everything else should be consistent. So we plug in the numbers as we do. We're not going to have to do an anti-log or anything this time. So, our life is reasonably not too complex here. We're just going to solve for the natural log of this ratio, set it equal to these numbers, and solve for EA. EA is going to be 208 joule per mole. Why joule? Well, because our constant, again, is in joule. We could convert this to kilojoules if we wanted, unless we're asked for kilojoules in the question, where we can happily leave it alone. This is really all there is to the Arrhenius and the Van Hoff equation. Important stuff for understanding our chemical reactions and what it takes to get them over the hump. But basically, this is what you need to know for this particular topic.